In this last third learning sequence of block 3, we will talk about multiple linear regression. So what to do if you have several x variables, what to do if you have several predictors. First of all, let me just make a short introduction. So in the previous learning sequence, we discussed what to do if x and y are single variables, right? So you have one y and one x. Of course, if you have several y variables, for example, you want to use height to predict weight and to predict shoe size. So in this case, you have one x variable and two y variables. In this case, you can simply build separate models, right? So you can make one model for every y variable. There are also other solutions. You can make one single model for that, but this is beyond the scope of our course. So far, we will just simply use separate models. But what to do if you x multivariate? So if you have several predictors, several x variables, in this case, you need indeed use a special method which is multivariate calibration or multivariate regression. And that's exactly what we are going to do in this learning sequence. I must say that there are many different methods to fit multivariate regression model. You can see just some of those here, a list of the most known probably. The first three methods provide you a linear model. So it's three different ways to get a linear regression, a multiple linear regression. And the last two provide you a non-linear model. There are also some other methods as well. We will talk about the simplest one, multiple linear regression, but later, if you want, you can also learn the other ones. Okay. So multiple linear regression, formally it's defined like this. You have one y, and then you have several x, right? So in this case, let me use p. I think I will use p also later. So you have p x variables. In this case, the model is a multivariate relationship. So you have a function which gives you the multivariate relationship between x and y. And if this function is linear, meaning y is a linear combination, is a weighted sum of x variables, then the regression is linear. But if this function is nonlinear, so you have nonlinear term like quadratic term, exponential term, and so on, then the regression is nonlinear as well. And this is just some examples, right? So you can see this is a linear regression with p equal to 2. This should be p. So you can see you have x1, x2, so two predictors. And then you have also intercept, of course. This is the real y values, these are residuals. Everything that we had before, we just added one additional term for x2, right? And then if you have like more than 2, then you simply add additional term for every predictor that you have. And the regression coefficient, this regression coefficient for this predictor is simply estimates of effect of this predictor to predicted y values. Okay, but you can see that y, for example, nonlinear regression can be tricky. If you use polynomial regression with polynomial degree 2, you can see you already have a lot of additional terms. So you have a linear term, quadratic term, linear term for x2, quadratic term for x2, and then you have also interaction, which we'll talk a little bit about in this learning sequence as well. So nonlinear regression in case of multivariate x variables, so it can be really, in case of multivariate x, can be really, really complicated, right? But in this case, we will talk about only the linear part. So this is the model, linear regression. If you don't have intercept, for example, if you center the x and y, if you subtract average of x from x values, and if you subtract average of y from these y variables, then you can just get rid of this one. And this is the model. And in this case, I can actually make a very short notation. It will be a matrix form notation. You probably know the linear algebra already. So in this case, this is the matrices, right? So these are all your y values, just a single column, just one variable. In case of x, you have p columns, right? Because you have p x variables. And then you have p regression coefficients. You remember, you multiply row of this matrix to column of this matrix, and then you add the residuals. So every single data point has also residuals. So this is the matrix form. And then actually, if you know linear algebra, you know that how to find the solution of this. You simply, I will just briefly show you that. It's not necessary actually, but I'll just do it. So you multiply both sides to transpose the x. Why? Because xtx, this matrix, is a quadratic matrix. And then if x variables do not correlate with each other, and this is one of the requirements for linear model, then this will be also diagonal matrix. And then it means you can make an inverse. You can find an inverse. So you now multiply xtx minus 1, xt y, and then you do the same here, xdx minus 1, xdx b. And then you can see that when you multiply matrix to its inverse, it's just identity matrix, right? It's like 1 in the normal multiplication. So that gives you a solution. So b equal to xdx minus 1 xdy. And actually in R, you can find this solution using just one line of code. Of course, we are not going to do it manually, but just to give you an idea that you can indeed make all these computations just using linear algebra. Okay. However, this inverse exists only if number of columns in X does not exceed the number of rows. Otherwise, this matrix will not have the inverse matrix. So that's one of the limitations. You need more data points than number of X variables you have. If you also use intercepts, you need by one more. So for example, if you have 5 data points, you need 6. If you have 5 variables, you need at least 6 data points, or actually more, because you also need to estimate residuals. Okay. But as I said, we are not going to use linear algebra. We will use a software for all the calculations. So it's just to show you that this is not a magic. It indeed can be solved by using mathematics. Okay. The solution, if it's a linear regression, it's a plane, or we can call it hyperplane because it can be also more than 3D space. So in this case, you can see I have x1, its height, x2 is IQ, and then I predict weight, right? Rather stupid example. IQ definitely does not depend, weight definitely does not depend on IQ, but it's just to show you this illustration, okay? And then you can see this is actually people data. I just standardize it. We will talk about standardization in this learning sequence as well. And then you can see, for example, this is the predicted value, this is the real weight of person, and this is error of prediction. Okay. Because you have many X variables, but only single Y, and the model also gives you the single variable with predicted value, so you have Y and YP, it means that you can reuse all the knowledge that you gained in the previous learning sequence about estimating equality of your model, right? So you remember that we just simply take error of prediction, y minus yp, and then we do all the statistics, we calculate all statistics based on the error of prediction. So it means that we can make predicted versus measured plot, we can make plot for residuals, both checking randomness and normality, we can compute R-squared, we can compute standard error, and we can also make an F-test, okay? So all the things, all the knowledge you gained in the previous learning sequence also can be applied for the multivariate regression. Okay. The only difference here is that you will have several regression coefficients, and we will talk about regression coefficients, how to understand them, and also what to do to make them a little bit more robust, more interpretable in this learning sequence. And then example, you remember the previous learning sequence in the last video where I used R to do something. I predict income based on age. What if you make a multivariate model? What if you predict income based on 2 variables? For example, age of person and the region this person came from. So you can see that if I make just the simple models, right? Age depends on income. This is what you actually had before. So this is the correlation coefficient, and this is the linear model, right? This is how age depends on region. And you remember region in this case, it's a categorical variable which we turn to numeric by taking +1 and -1, right? So this is the region. So you can do this trick with any categorical variables. And then you can see that, of course, it's stupid to calculate correlation here because X is not continuous. But if I do that anyway, you can see that the correlation is minus 0.45. And then you can see a very big spread of the salaries here and here, right? But there is an effect. You can see there is an effect from region. And maybe adding region as additional variable can help to predict income better. So let's check it. So this is, I will first make a univariate regression. I will just repeat what I did also in the previous learning sequence. So I read people data. I make a linear model based on just one single variable. So this is Y, this is X, right? So I predict income based on age. So it's simple linear regression. And then I show summary. So this is the summary. You can see the intercept, the slope, the standard error, the R-squared, results of F-test, everything what we also did in the previous learning sequence. So now I will make it compact. It's not exactly the R output. I just made it a little bit compact in order to compare it for future. Okay, but it's the same. So you say regression coefficients, standard error, R squared, F test, and so on. Okay. Now let me make a multiple linear regression model. And it's very easy. You simply add additional terms. So this is x1, this is x2, and this is y. So you can see the rest is the same. But now let's look at the summary. Look at this. Now we have one intercept and two actually slopes, right? So the first slope tells what happens to income if you change age by 1 year. The second slope tells what happens to income if you change region by 1. But you remember, region goes from -1 to +1, right? So it means that if you want to see the difference between two regions, you need to multiply this by 2, right? Because regression coefficient always tells you it's a slope, right? What happens to y if you change x by 1. Okay, but what is important is that all these statistics look much, much, much better. Much better. So let me compare this. Look, first of all, the effect from age is a bit different, because now partially this effect is somehow explained by the region or by the intercept, so the model is different, so therefore the effect is a little bit different, but you can see it has the same order of magnitude. It's approximately 800 euro, right? But look at this one, standard error, twice smaller, more than twice smaller. R squared, before you could explain 78%, now you can explain 95%. So what it means? It means 78% of variation of salary, the variance of salary in our sample, depends on age, but 95 minus 78, which is 17%, 17% of the variation of age is related to region. So it's related to the fact that we have people from two different regions. And then you can see the F value is also more than twice larger, and the P value is really, really small. It's almost 0. Okay. So adding additional variable in this case, because indeed this variable has a correlation, has a relationship with y, improves the model a lot. Okay. Let me show you a couple of plots. So this is predicted versus measured plot for the univariate model. We already have seen it before. And this is predicted versus measured plot for the multivariate model, where we have two variables. You can see how closer points are to the straight line, so the variation is much smaller. Okay. And then you can see again the statistics. I already mentioned that the new model is much better. And then you can see that this is the simple linear regression model and multiple linear regression model. Okay. So this is the residuals plot. So these are residuals. These are predicted values. Residuals, predicted values. Also, you can see that the pattern is more or less the same. They look both random, but the variation of residuals is twice smaller in this case. And this is the normality plot. You can see in both cases the normality plot looks fine. So it means that we cannot reject the normality assumption of residuals in none of these two cases. Okay. Now, you probably notice it that when you look at the summary, there are two R squared values. The first just R squared, and second it's called adjusted R squared. And the adjusted R squared is always a little bit smaller than the normal one. What is adjusted R squared? Adjusted R squared is a penalty that you have by adding additional variable. The idea is following: if you add additional x variable, if you add additional predictor to your model, even if this predictor doesn't have influence on y, your model will get better. Just because you account for this additional variance in your data, although it's maybe random variance. In order to compensate this effect, we use adjusted R squared. How it is computed? This is the computation. So this is normal R squared. And you remember, this is the error variance, right? So this is error variance, residual error variance, right? It's a percentage of error compared to the total variance of y. And we simply increase it by taking the ratio between, you can see, sample size -1, and then sample size minus number of variables -1. And then if you have more variables, this value will be smaller, and it means the ratio will be larger, and it means the error, this additional penalty, will increase the error variance and decrease the explained variance, which is R squared, right? You can also compute it based on the additional R squared. You remember that this one, this SSR divided to SS dot, it's the same 1 minus the normal R squared, right? So this is what I use here, and then you multiply this ratio as a compensator and then subtract from 1. Okay. Let me show you how it works. So this is the the values I got from the R. Let me do it manually now. So this is the expression, how to use it. Let's take the first one. Look, this is the R squared we got, the normal one, the conventional one. This is n, it's a sample size, it's how many data points I have in my people data, it's equal to 32. This is just 1 because it's one variable. You remember this is number variable. So this is the simple linear regression model, one variable. So it gives me the ratio of 31/30, and it gives me a little bit smaller R squared adjusted. Now the same for the second model. In this case, we have original R squared is larger, but when we compensate, you can see we write 2 here. So now this ratio will be 31 divided to 29. So you kind of make this ratio larger because you add this additional variable, and it makes the error term a little bit larger, and consequently it makes the explain it part, the adjusted R squared, a little bit smaller. So this is just a compensation for having more than just more variables in the model. Okay. Well, that's how to compute it, and now you know the benefits of using multivariate regression model over simple linear regression. And of course, these benefits, you can gain these benefits only if indeed all these variables have an influence of y. Okay. Now, in the next video, we will talk about how to interpret regression coefficients.